Hey stars, welcome back to a new video. Today we are going to break down the basics of RF transmitters and receivers in a simple and beginner-friendly way. And if everything goes well, I even test a few circuits for you. So, stick around. A few years ago, I uploaded some videos on this channel where I explained that the sound signals we use for speaking, like my voice, are low frequency signals. And if you were to connect a microphone directly to an antenna, the signal just wouldn't transmit. Physics simply doesn't allow it. In fact, without taking the laws of physics into account, we'd need an antenna the size of 3 Burj Khalifas to make that work. Clearly not practical. So what's the solution? We take that low frequency audio signal and combine it with a much higher frequency signal. The high frequency one is called carrier, and the lower frequency one is the message. The message signal modifies or shapes the carrier signal. This process is called modulation, and there are several types of it. For example, AM, FM, FSK, ASK, and so on. In this video, we will only test AM modulation. And if you enjoy this kind of content, I will explore other types of modulation in future videos. So let's dive in. Alright, as you requested, I'm going to demonstrate AM modulation using simulation software. This simulator is Porteous, which is more accurate than others like Multisim, and most electronics experts prefer it. Now take a look at this circuit. If we connect the carrier signal to the collector of a transistor through the resistor, we will see the exact same signal at the output because the transistor is off. But if you apply a square wave signal, which could be a digital message signal like the output from Arduino pins or temperature sensors to the transistor's base, the carrier signal at the output changes shape. This type of modulation is called ASK, and it's very simple. Check out the output waveform. Now let's replace the square wave with a sine wave as our message signal. At first, the output still looks a lot like ASK, because the transistor only turns on when part of the signal is strong enough to activate it, and then it quickly goes into saturation. Also, it completely ignores the negative parts of the signal. So what does that tell us? It means we need to bias the transistor properly so it stays in the active region and can respond to both the positive and negative swings of the input signal. Here's a circuit I've always used for signal amplification, and it's worked really well for me. I'm connecting a 1 volt amplitude carrier signal to the base of the transistor. As you can see, the output signal is slightly amplified and not clipped, which is a good sign. Now if you connect a capacitor between the emitter and ground, the amplifier's gain increases significantly. But in this setup, we are not trying to amplify. We want to modulate. Next, we need to apply the message signal in a way that it affects the current flow between the collector and emitter, where the carrier is flowing. So I disconnect the ground from here, and instead of grounding it, I connect the message signal. Let's set the message signal to a 0.5 volt amplitude with a 1 volt DC offset. Now let's look at the output. We've just built an AM modulator. Now the question is, how do we demodulate it? Alright, before we go any further, you've probably realized but know that getting a high quality AM signal really depends on the amplitude of the input signals to the modulator. And building this physically requires the right measuring tools. So here's what I'm thinking. I want to start a challenge where we build those essential tools ourselves. But there is one condition. Hit the like button right now so I know how many of you are on board with this idea. And if you haven't subscribed yet, don't forget to click that subscribe button too. Thanks a lot. To demodulate the message signal, we need to separate either the positive or the negative half of the waveform. I do this using a diode, but not just any diode like the one you see here. You need high-speed diodes for this task. After that, I add a low-pass filter. Now the message signal is demodulated, but the amplitude is weak. That's because we forget about impedance matching. On the modulator side, these two resistors are in parallel, which means the output impedance of the circuit equals the smaller resistor, which is 1 kilo ohm. So all we have to do is change the input resistor to 1 kilo ohm as well. And that's it. Oh, by the way, the same method works for demodulating ASK signals too. Let's get hands-on for a bit. I bought this 8098-3 module a few months ago and already managed to set it up. With the Arduino software, I was able to observe the output waveform. But there are some limitations to viewing the signal that way. So I asked a friend to lend me his oscilloscope. As you can see, not only did I amplify the output waveform, but I was able to visualize it much more clear. I'll explain more about this setup in the next video. Now let's go ahead and implement ASK modulation, just like I explained earlier. I set the carrier frequency to 530 kHz and use a 200 Hz square wave as a message signal. The message signal is generated by a 555 IC, which I've also made a video about. It has also been tested in simulation and works perfectly. For demodulation, I'm going to use a regular AM radio. Alright, let's test it out and see how it works. Since the frequency is quite low, we need a large antenna. So when I touch the antenna, you can actually hear the demodulated square wave signal. I also changed the frequency a bit and found that the radio works better at 536 kHz. Honestly, this is an old radio, so these small errors are pretty normal, especially in communication circuits. Now let me turn off the transmitter. Yeah, the sound stops. And I'll turn the transmitter back on again. Perfect. Thanks so much for watching. Please don't forget to like the video. See you soon.